certain y, so di equal 1. It's a simple exercise in probability, and it turns out to be this value here. First course in probability. And then we have the density function of y conditionally on the fact that we observe y. And we have seen this before. It's the normal density times the perturbation factor. So combining everything, the log likelihood is of this form here. There are two components. For the subject that works, that is di equal 1, we have the probability of observing di equal 1 times the conditional density, plus the second factor which comes from the individuals that do not work. And this can be rearranged, swapping the roles of these two. So this is the density of y times the conditional probability of observing 1 given y. And this factor here is what we compute. And the ingredients are this expression, but don't worry so much about the technical expression. Fine. Some remarks. Using this likelihood, we adjust essentially the original normal density as a likelihood function so that we inference withdraw this actually bias corrected. And this technique is widely applied in socioeconomic literature. If you search the literature for Ekman model, selection model, you find several hundred, possibly thousands. There is a criticism to take today that the outcome is strongly related to the normality assumption. So the perturbation factor of the normal density, which expresses the dependence on U, is strongly linked to the joint normality of components. And if you change that assumption, you change the perturbation factor, you change the unit. So there is much criticism and that, and therefore work to adjust them. And one route which has been attempted is via a semi-parametric or non-parametric approach, which is theoretically appealing, but in practice not much used because it requires a huge amount of data that often is not available. Another direction is via robust, sort of robustified likelihood, and there are some works in this direction. Other works is more specialized because the main case, important case outside normality arises in connection with the discrete response variable. But in many other contexts, you can still use methods developed for the normal even for discrete variables. Often they work. But in this case, everything is it's less robust. It's more sensitive to the correct assumption. So you have to develop other specific methods. And some are being developed that they're always quite focused kind of proposal, working with a specific function, but for a specific set of assumptions. An alternative route, which is being developed quite actively in recent years, is via CoE. CoE allow wide range of flexibility in the choice of the dependence. So, while the corporate fraction, one can introduce various forms of dependence between the target variable and the U, the vector variable that regulates sensor. So this is the framework, the broad framework where we are operating. So what are we going to do? Well, we see in a moment that this construction, this original normal case construction, Bruno and Heckman, has a direct connection with the branch of literature in Symmetry-modulated symmetry or skew symmetry formulation, and I'll explain better in a moment. And building from on this connection, we develop a general form of construction for selection distributions, which works in parametric context. Since it's parametric, does not require necessarily thousands and thousands of data to use. And at the same time, there is a wide margin of flexibility and adjustment in the assumption. So it's not focused to one specific situation. Although operationally we focus on discrete distribution, but still within this discrete distribution there are many options. Okay, so this is the end of this long introduction. Let's go to the connection with modulated symmetry. Now, we have seen this expression before. So the normal density times the perturbation factor. And if you move this expression into another context, it takes another name. In the context of skew distribution or symmetry modulated distribution, it's called extended skew normal. Skew normal because it's normal times something which makes it non-symmetric. And extended is because it's an evolution of original form which was not extended. And this is an instance of a general construction very much in use, say, within continuous type of distribution, where we take a density, we multiply by this factor gx, which is explained, and then we normalize. And gx is the probability that every sample a certain value x from y, then we observe it. So from the density f, we sample the value x, and then we decide we observed, we put in the sample, or we throw it away. With probability g of x, we put in the sample. Otherwise, it's lost. And phi is the expected value of this thing here with respect to the density f. So this term in the denominator is the correct normalizing factor. So this is the general form which is familiar in a certain area of literature, because under some simple conditions, especially that f is symmetric, this facts hold. So you don't have to worry about computing this integral and computing this integral, the connected integral, which can be hard to solve. And the construction allows multivariate extension very easily. And there is already wide literature in this area, which is summarized in this monograph. So no more However, now we move it in other directions. Slightly. So we use this type of expression, but we adopt it in the case of non-symmetric action, which is the main topic of the earlier slide. And also, F may be discrete distribution. So then we run into this technical question exercise. The pure is suspected, which in some cases is doable, in many other cases not so easy doable. Of course, in the discrete case, there is always a simple solution. Just sum up. The integration boils down to a summation. In the continuous case, you can use numerical integration. There are some favorable cases where you can actually work out the integral, but not that many. So, what about the log likelihood? The log likelihood is exactly the same as the structure of what we've seen before. The difference is that this part here, which can be rewritten, this is exactly what you see 2 slides ago, or 3 slides ago. And this can be rewritten this way. The only difference is that G here is in principle anything. So these 2 components before were the normal density and a normal probability. Now they can be anything. As I said, the simplest case is with some discrete distribution, and the very simplest case is binary. So consider now only 2 possible values for y, 1, 0. And in this case, the probability of 1 is also the expected value of the binary, this elementary binomial distribution. And pi is just this sum here. If you once you specify the function capital G, then this is elementary. And if the expected value of y depends on covariance, which is the practical case, then things change only slightly. So mu I, instead of being a constant, is a function of covariance. For instance, a typical case using a logic or a probability model is that mu I is the logic model is this expression, and the probability model is this expression. Typically, statisticians prefer the logic, and econometricians prefer the probability. Differences are not that important. Now, the question is still open. How we choose G? Well, G has to be a probability depending on the argument. And it's conceptually convenient to introduce a random variable T, say T as set a distribution function G0, and G of X is a combination of G0 times a function of Y, such that G of Y is the probability that capital T is less than this expression, H of Y, given model. Now this form of writing may seem restrictive, but in fact it's not. It can be shown that if, for appropriate choices of these 2 ingredients, G0 and H, you cover all possible cases. And of course, we want to incorporate covariates which regulate the selection model. And so this, in the Heckman model, there was this kind of expression. So the component of this goes into H. And here are some instances. One instance, say T, capital T is standard normal, and H is this form of linear predictor, which incorporates the covariates here, plus a function of y and this extra parameter alpha. So the combined expression is what is alpha? Alpha. Oh, so first of all, why we have the reciprocal mu here? It's not essential. It's only a way of standardizing mu. Since this is ui is the effective value of y, so we are only standardizing. So the real, say, important factor is alpha. Alpha is a parameter which regulates the association between y, the value of y, observed value of y, and the selection mechanism. But that is similar to the correlation parameter which comes into the original bivalent distribution. So instead of rho, here we have this alpha to regulate associations. Another example is this one. Say capital T is exponential. The exponential has a support on the positive outline. So h of y has to be positive, and therefore we put an x in front, and then we get this sort of expression. So g of y is of this. G of y is of this from here, which is essentially the Gumbel distribution. But these are only two possible cases. You can think many others, and ideally you could think one which is motivated by subject matter consideration, the phenomenon of interest. So you have possibility to incorporate subject matter consideration into the model, which I think I consider as an advantage compared to Computational. I've already talked about alpha. So another example, another type of discrete distribution very much used is Poisson. So here there is a misprint. This should not be law to be extra. Clearly. So standard assumption is y is a Poisson distribution with parameter mu, which is exponential of linear combination of the parameter and the covariance. And then they gain the same sort of selection mechanism and sensoring comes into action. We go through the same type of computation. In this case, the summation cannot be completed at infinity, but we have to truncate. Of course, we truncation point which is high enough to embrace almost much as possible of the mass, something very close to 1. And then we have to choose the option for G, etc. And similarly, you can use negative binomial and other distribution. So on. It's literally the same. It's only the mathematical expression density switch. Oh, okay. I think I skipped this. I wrote it a very. Let's go to this computational aspects. So, there is a group. There are two groups of parameters. Alpha, which regulates, which is just one number, which regulates the association between the two components, y and u, or t, capital T. And then we have a bunch of regression parameters, beta, which are the main point of interest, the gamma, which regulates, which combines with other covariates, affecting the selection mechanism, and possibly there is an extra parameter, such as could be the negative binomial. We have an extra parameter which regulates variability. Dispersion. In the context of generalized linear models, called dispersion parameter. So what we can do is the following: to consider profile log likelihood, that is, for any fixed value of alpha, we maximize with respect to the others. And you can evaluate over a grid of values, or actually preferably starts with some sensible value where alpha is 0, and therefore if alpha is 0, you have two separate generalized regression models. In the binary case, you have two separate logistic regressions. That provides initial value for beta and for gamma. And starting from then, you search the parameter space, and the search can be fairly effective because we worked out first and second order derivatives of the log likelihoods. For any given alpha, we have the expression of first and second order derivative with respect to the remaining parameters, these other parameters here. Therefore, the numerical optimization technique can be fairly efficient. So at the end of the process, when we repeat this process for various values of alpha until we find the maximum point, and since this is a one-dimensional search, again, can be fairly effective. And then associated with that, of course, there is a set of and the same expression which are used here, of the second derivatives, can be used to compute the Hessian at the maximized point, therefore providing observed information metrics. Now, I don't want to enter into much numerical details, but at least in one illustration is important. We have taken this data commonly associated to a certain publication. And this is a data set which has been used already in this literature, specifically the people that have made a proposal for binary response. And this refers to the German preferences, the preferences of German people about access to the So the response is why the self that I makes at least one visit to the doctor every year. But people can subscribe to the public service or not. They can have independent kind of assurance. But for those that go to independent assurance, you don't know, they don't know what happened to that. And as I said, this data are being used by other people, specifically this gray, which is standard textbook in econometrics. Using the technique and we also fit the model described here. The findings, the good thing is the general findings are similar to what they obtained. And so far, you say, well, so if you get similar findings, what's the advantage? Well, at least one advantage is this. But first of all, this technique, specification, is one instance within the broad family. So it's a good assuring that in one case for which there is an answer, we produce a similar sort of answer. So hopefully, if the method is applied to other situations for which there is no solution, no proposal, then hopefully, well, there is positive indication of sensible answer. Then, another indication that we have connects to the previous remark that Heckman model is very sensitive to the assumptions on the underlying sensory mechanism. So here we try two different assumptions on the sensory mechanism. A couple of slides before I said instance A, instance B. There were two different assumptions. And what you see here is the profile likelihood plotted versus alpha. So this is a parameter which regulates association. This is the profile likelihood with respect to all of the parameters under two different, quite different assumptions of the underlying sensory. This is a normality assumption. This is a Gumbel assumption. As you see, the indication is very much the same. The curves are very much the same. The maximum is almost identical. And if you construct confidence interval by chopping the curve at a certain level, then by chi-square distribution, so this is 3.84, this is level, you get about the same interval. Not exactly the same. You see the endpoints here? This is a bit more than -5, and this is a bit less than -5. Well, this is, in this case, the difference is equal. So there is an indication of stability. That's simulation. We've done a lot of simulation. I don't attempt to present all of them, but only sketch the range. So we go with binary and for so it says O, but it's actually and for so on. And selection is either type A or B, which is summarized here as normal with linear H or exponential with exponential H, which translates into a Gumbel with a linear H. In the simplest case, the mean of the response variable as this linear expression, and the mean of the latent sensory variable as this expression. Then there are variants. One variant is related to the problem of exclusion restrictions. In that literature of selection model, there is a big issue about this condition. It is required that there is an extra coordinate here which does not appear here. Otherwise, you run greater difficulty. So a variant is to chop off this component. Or another variant is to increase the number of active components. There are only, here there are 2, here there are 3, but up to 6, 7 for each side. So, and also, and that was quite challenging thing, we generate data from an entirely different kind of stuff. Originated from the copula model. The key findings are that that's the important thing. The estimates of beta remain essentially unbiased, even if you do not satisfy this condition here. So even if you drop off the term here, and even more importantly, perhaps, even if you sample from this completely extraneous model. So even if you miss completely the underlying assumption, still the key component, these parameters here, are estimated essentially unbiased. So summary remarks. So we are wrapping up. So the proposal is quite flexible. You can choose various ingredients quite freely. So it allows many specifications. And I stress once more, if you are able to formulate from subject-mathematical consideration an hypothesis on the sensory mechanism, you can it's particularly suited for discrete response variables. It works also outside there as extra computational. And the good thing is, well, one good aspect in my view is that response and selection equation can be chosen separate. That my conjecture is that this is also the reason why the estimates of beta are so robust. And as already mentioned, yeah, there is this essential robustness, it's a form of robustness with respect to the misspecification of the sensor. And here are some references that I made presentation. And about this paper, there is a preliminary version 2 years ago, which was fairly developed stage, but after that we have done some extra work, and this final version is going to appear in this journal. So I targeted to 50 minutes, and I've taken 46. So we say thank you for your attention.
Thank you very much, Prof Adelchi. Open the floor for some quick questions.
Warren. Thanks for that lovely talk. So my understanding that you're effectively trying to count something without knowing what the underlying objects are. So you've got some small subset of things that you want to count, and then you have a collection of hidden variables or variables you can't measure or you can't probe. And then it seems that things get worse when you introduce the regulator variable alpha. Now, alpha should have a physical interpretation. That must be, because it's entering and because it enters the equation, it seems to control the distributions, specifically distributions defined on counting objects, where now you already don't have all the information about what's affecting the way that you count things. Your regulator should have some kind of intrinsic meaning. It should have a nice physical interpretation. What is that for your regulator alpha?
First of all, a remark on the initial part. We are not actually estimating the underlying values. The y's which have not been observed are not estimated. Maybe it can be developed further, but for what I presented, the target is to estimate parameters data. So, which regulates the association between the covariates x and y. So in the case of the women wages, so what is the relationship between, say, education, age, etc., with the salary that you get? That's the target. Not individual, the salary of the individual. As for the remark that alpha should have a physical interpretation, I agree, I underline that this is, in my view, an advantage, the fact that you can build a model for essentially mechanism that incorporates this Symmetry-MaSS consideration. That's great. As it is, see whether I can pick up the right slide. That's what the sensory mechanism is regulated by this function here. If the distribution of y of interest generates a value little y, this function expresses the probability of retaining the value or throwing it away. And this can be shown that this can be written in this form. Whatever this G, it can be written in this form, which already has a nice interpretation. It is the fact that certain under variable G is below a certain relation. Now, for the more specific sort of interpretation, one has to write down an expression like this, for instance, or something else. But that really depends on the specific problem. And there's no way you can write a universal expression that is feasible for all possible problems. What is provided here is a general framework which has to be adapted to the specific situation.